Okay, this time we are going to add 3 angular momentum to our system. So far, what we have seen? Well, we have seen how to add just 2 angular momentum. We consider the specific example of having 2 electrons in the same system, and we described what is the basis of states that describe that system. Now, in the process, we just learn how to relate essentially two bases for that system. This is what we did from in last lecture. This time, we are going to consider now, we are going to assume that the two spins, the two first electrons, are in a given state, and now we are going to add the third electron into the system. And for it, we are going to consider two distinct bases for it. Well, the first one is just the tensor product of the both bases, and the second one is going to be the new basis, which considers the total angular momentum of the system. Well, these two bases now must be related. So, in what we are about to do in this lecture, well, it's going to be very similar to what we did in previous lecture when adding just 2 electrons. You see, last lecture, let's just recap a key idea. We add 1 electron, so 1 electron in the system. So this is the system, this is the electron. And the electron, the spin state of that electron was some ket living in J1 is equal to 1F. That's it. That's where it lives. Now, you have a second electron which lives in E, J2 is equal to 1F. And then you just add it. You just take the tensor product. Well, you consider a new basis for that tensor product space, and then you constructed another basis for that tensor product space, and then related both. So, what we did was essentially writing, well, you just construct E1 tensor with E2, and found two bases for this thing, and then relate those. What we are about to do is something like this. We already have a system with 2 electrons. Well, we have here the E. Let's call it this one, so 1, 2. Let's call this E 1, 2. So we have the E 1, 2 here, and then we have a third electron, which let's call it E3, which is again J3 is equal to 1F because it's an electron. So the quantum number J3 is 1F. Now this time, what are the states in which my 2 electrons can be? Well, here it was described by the quantum number J1 is equal to 1F. But this time I'm going to specifically choose the quantum number S12 is equal to 1. So, in other words, these 2 electrons must be described by some linear combinations of the triplets that we found in last lecture. Okay? Just like when I say I want this electron to be described by J1 is equal to 1F, meaning either is a combination of these states. So, what I mean by saying this electron is described by some linear combination of C1, for example, and then M1 is equal to 1F plus C2, M2 is equal to minus 1F. So the state of this electron is some linear combination of the bases. Well, but we specified it was J is equal to 1F. This time, I'm specifically saying that I want these 2 electrons to be described by some linear combination of the triplet states, which was 1, 1, plus C2, 1, 0, plus C3, 1, minus 1. Well, by the way, what these entries mean, well, this is the first entry. It was S12, and this was M12, and so forth. So this is what I'm saying. These 2 electrons, I want their spin state to be described by some ket in that space. And of course, when the electron is a single electron isolated, well, That state is also described, well, by some linear combination. Let's call it alpha. M3 is equal to 1f plus beta. M3 is equal to minus 1f. So this is our starting point for the lecture today. We are going to consider two electrons described by this and one electron described by that. And now, when I join this electron to these two, I want to construct a basis that describes the three electrons. In fact, I want two different bases for it. And then let's rewrite the two bases, just like we did here. We described here the states for this system. We constructed a basis for it. The same thing for this one. We joined the two. We constructed a new basis, which was the basis for E12, which was the tensor product. We constructed a new basis for this space, so we have two, and rewrite them, just like we are about to do here. So essentially, to sum three angular momentums in quantum theory, you just need to understand very well how to sum two. But we already learned that in the last lecture. So this time, let's just adapt some of the ideas that we already used in the last lecture, but to this situation. So let's construct the first basis for the tensor product between E12, S12 is equal to 1, and tensor with the E, let's call it 3, J3 is equal to 1F. Well, we already have the basis for this state. Here they are, and we already have a basis, these two cats, for this space. So let's take the tensor product of both. So the tensor product has the following form. So it's a set of the following cats. So let me write it. It is S12, M12, tensor with the M3. Is it fine? Well, where S12 is 1, specifically 1, M12, well, must be either -1, 0, or 1, just like we derived in last lecture. So all these details come from last lecture. Well, this, by the way, comes from the first lecture, where we said that this thing is either -1f or +1f, or plus or arrow up or arrow down. But we chose to adopt this notation. Okay? So here you have a basis for this state space. So any linear combination of states like this describes, well, the spin angular momentum of the three electrons. Now, let's now introduce, but before going into that, let's just make a picture, that summarizes this information. So this picture, very similar to what we saw in last lecture. The picture is as follows. On the horizontal axis, let's write here the M12 and here the M3. Okay? So the M12, it could either be 1, 0, or -1. While the M3 is either +1f or -1f. Now, each one of these dots that I'm about to write, here, and here, here, and here, and here, and here, represent one of these basis states. Because you see, S12 is always specifically 1, so the only changing numbers are these ones. Well, and this diagram covers all the possible combinations. So, this is just a better way of describing the basis than this thing here. Now, let us introduce some operators that act in this space. And those operators, so those observables, let's list them into the following set. So is S squared. Let me just write it like this. It's better. S12 squared S12 Z, and then S3 squared S3Z. This finishes the set, but there is still something here that I need to specify. You see, because we are specifically talking about electrons, so I need to provide this information. So S1 squared and S2 squared. Can you see? So let's assume that we have this set of commuting observables. So we have these CSCO. You can check that they all commute. And by the way, each one must be understood as extensions into the tensor product, just like we introduced last lecture. Now, if all these observables commute, then I can construct a basis whose elements are eigenstates of all these observables simultaneously. As a result, I can label that eigenstate by the corresponding eigenvalues, or better yet, by the quantum numbers that determine those eigenvalues. So let's write that basis. So it's this cat. Well, the quantum number that describes the eigenvalue of this observable is J1. For the second one is J2. And now for this one, well, is what? It was S12. For that one, it was M12. And finally, here we have J3 and M3 for that one. You give me these three numbers, well, you just zoom in, you just gave me a specific cat of the basis. Of course, this is 1F, this is 1F, this is 1F, so usually one suppresses this from the notation. Moreover, because we are specifically talking about S12 is equal to 1, we can additionally suppress that one. So we usually are going to write this just as M12, M3. Okay? You need to remember now, from the context, what are the remaining. First, you need to remember that there are other quantum numbers for this. And you also need to remember the reason why they are not written, because their number is already fixed. Now, so far so good. This is how you label the basis that results from that set of commuting observables. Well, but this basis is related with that one quite easily. Okay? The relation is as follows. We know, but before going into that, let me just say something here. Now, let's move into it. Let's relate this with this. So I think it's easy to see, because this is just a labeling of the cats. So this is just a tensor product that you decided to take, to construct it. Here, now you have to relate this thing with that thing. So the relation is, well, I think it's obvious. You're going to be M12 tensor with M3, where I already suppressed this thing here, because again, it's fixed at 1. How do I know this, by the way? How do I know this is a good idea to make this assignment? Well, because these observables can act on this basis. Can you see? These observables, you see, if you go one by one, you act with these observables on these cats, well, what you recover are the eigenvalues that you decided to assign, or the quantum numbers that you decided to assign to this thing here. Okay? And so, there must exist a correspondence like this. Okay? I think it, I don't know if you can see it clearly what I'm saying, what I'm meaning. Okay? To make the correspondence, just act with this on that, because these are also eigenvalues, eigenvectors of those observables. And the eigenvalues that you get are the same eigenvalues that you would get if you act with these observables on that one. So these cats must be these cats. Okay? So you just give a new meaning to this thing. Okay? You just gave a new meaning to thing. If you did not have this, forget about it. This is as far as you can go. You just label the basis. But if you want to give more meaning to it, well, you need to rewrite this basis with something else. And you can do it, but just by acting with this on that. Well, I'm not going to do it because it's quite tedious to write this thing, and it is not the focus of the lecture today. But you can do it. Act with this on that. Always remember that these must be understood as extensions into the tensor product. Moreover, there is something else here that I want you to remember. I already said it, but I want to stress how important it is. This cat here, you must remember last lecture, can in turn be written as some linear combination of the cats, of the tensor product of the cats, of the individual spins. Because again, remember, this is an element of the triplet. Very important. Soon you are going to use it, that fact, at the end of this lecture, but is element of triplet. So in turn you can substitute here some linear combinations of M1 and M2 cats. Okay? So far so good. Now, this is our basis. This is our description of the basis. That's fine. Now let's introduce a new basis into this space, into the E12 tensor with E3. Well, for that we need a new set of commuting observables. So let's define them. The new set of commuting observables. Maybe I should... well, let's do it here. So the new set is, well, first let's write the important part. It will be S total squared S total Z. And of course, we need to specify S1 squared, S2 squared, S3 squared, and S1, 2 squared. All these observables, as you can check, I'm not going to do it because it's again a tedious task to do it. All these sets form a CSCO. They all commute. What is S total? By S total is easy. So the vector S total must be S1. Let me write it like this. S12 plus S3. But what is S12? You need to remember from last lecture is S1 plus S2. So you get here plus S3. Again, this is a vector whose entries are operators, which, by the way, must be understood. Each one of those operators must be then, in turn, be understood as extensions into this tensor product space. Now, of course, if they commute, you can construct a basis of which are eigenvectors of all these of these operators. So let's define that and write it the basis as follows. So, well, let's go one by one. So you have J1, J2, J3 here, and then the big S 1, 2, like this. And then, this is new now, is going to be the S total and the M total for that one. You see, why do we need all these observables? Why isn't these two operators just enough? No, you need all the others, because you see, each one of these operators essentially are specifying a quantum number that is important for our system. So, for example, this one the quantum number is J1, which in turn tells you that you are talking about spin 1f particles. The 2 is also spin 1f particles, so you need to include that quantum number. The same thing for the 3. So the fact that we are dealing with electrons, which have spin 1f, well, is essentially encoded by using these 3 operators. So we want our bases to be eigenstates of these 3 operators. Similarly, when we spoke about the 2 electrons on the system on which we want to add the third, well, we want to specifically consider those two electrons to be on the state of the triplet. But that means that S12 must be equal to 1. So I'm specifically working with that. Well, of course, you can work instead with you can consider those 2 electrons to be in a single state. In that case, the S12 would be 0. But this is not the situation we are considering. We are specifically considering the 2 electrons in the first system in being on states of which are linear combinations of the triplet. So we need to specify this quantum number as well. Now, this is just a sum. The sum describes now the magnitude of the angular momentum of the intrinsic angular momentum of the entire system, and the z component of it. So we need these 2 quantum numbers. Of course, these are just a result. You see, in the first lecture of this series, if you remember, I just described what is the general properties of any angular momentum in quantum mechanics. In this case, you can see that S total is just a specific example of the J that we specified in that first lecture. Well, so, as a result, you need these 2 quantum numbers, where specifically, we also know that M total must be between minus S total and plus S total. This much we know. This much we know. Well, we also know this, so this is known already. So this is background information, essentially, that we know. Just like these operators. These operators just provide us the background information, on top of which we are going to sum everything and construct a basis for that situation. Now, we know this. We do not know what is S total. We do not know what is M total. But we need to figure it out. So, let's try to do it. And the strategy that we are going to use is very similar to what we did in last lecture. Because you see, this operator S total Z, you must remember now, the S total Z. What was S total Z? S total Z. Here. Well, you know what S total Z from this definition. It is the third entry into this operator. See? So S total Z is S1Z plus S2Z plus S3Z. But this in turn is S12Z. Fine. But you see, S total Z, by the way, I forgot to tell you something. This S total Z, let me write it. I need to write it before I move into this specific example. So, a very important detail regarding these 2 quantum numbers that I forgot to tell you. Again, all comes from the general definition of angular momentum. So this S total, when it acts on this basis ket, I'm going to suppress the known information. So S total, M total, again, important, is S total plus 1, h bar squared, and the same thing here. So this is an eigenstate of this operator. Similar SZ total, we know that is S total, M total, and then you get equal M total, h bar, S total, M total. So this is just a particular example of the J squared and JZ that we saw in the first lecture. where the quantum numbers now, well, have different notation. We are using a different notation. So that's it. And by the way, these two quantum numbers are related like that. So we know how SZ total acts on this basis, because this basis is the eigenstates of that operator. That's fine. So this much we know from the fact that it's a CSCO. But we want to go beyond that. We want to relate these states with the states for this CSCO. But for that, well, when the key ingredient that we found last lecture, which was, I was saying this, is that we know our S total Z, well, we know this is equal to S12Z plus S3Z. We know that. But because we know that, we know how to act with S total Z on the eigenstates of this CSCO, which are written here. Let's give a specific example of this. So S total Z. Let's act on this state, for example. This state was what? Do you remember? So you just read the graph. So it's M12 is equal to 1 tensor with M3 is equal to 1F. Okay, fine. But you know that S total Z is this summation. So S12Z plus S3Z acting on M12 is equal to 1 tensor with M3 is equal to 1F. Fine. But these must be understood as extensions into the tensor product. So this one is going to act just on that one, and that one is going to act on just that one. I spoke about that in the last lecture. So now I'm just using the final conclusions that we took in that lecture. So when that one acts on that one, it gives us M12 here. Specifically, it gives us 1, by the way. In fact, let me just do this in general. It's probably better to do it in general. Instead of specifically acting with S total Z on that one, let's do it in general and just consider M2 and here M3. So in this way, it works for everybody. So when this one acts on this cat, because this is already defined, we get M12 H bar. And when that one acts on that one, that's plus, you get M3 H bar. You see? And now you will just write M12 tensor with M3. Fine? Of course, you can erase this part and include here the H bar part. Is it fine? I hope you can remember, because in last lecture we introduced what was S12Z tilde, which was equal to the S12Z tensor with the identity at 3. So when you act with this on that, the S12Z acts on that one, and the identity at 3 acts on this one. So you get this number. Similarly, the extension of this into the tensor product, it was S3Z tilde, which was by definition S3Z tensor with the identity at 1, 2. So when we acted with S3Z tilde on this cat, well, the identity acted on this cat, and S3Z acted on that one. So you get M3, just M3. So this is what we introduced last lecture. Of course, I'm suppressing the tilde right now from the notation because that's cumbersome. You must understand what this thing is supposed to mean. Well, it's an extension into the tensor product. So you know how it acts on it. Now, from this, you see, because I act this on this, I get a constant times that. So these two things are the same. So m12 plus m3 h bar must be an eigenvalue, and this must be an eigenvector of S total Z. So every element of the old basis is an eigenstate of S total Z. And from that, well, we know what are the eigenvalues of S total Z. And this is key, because this number here, which I'm going to define as being M total, the eigenvalue that you find here, so by acting this on the old basis, I know all the possible eigenvalues. So I know all the m's, all the possible m's. So I know when S total Z now acts on these states that I defined here, that I labeled like this, I know what the M total is. Well, the M total is M12 plus M3. Okay? So far, so good. Now let's look at the graph and see what are the possible values for M total. I think it's quite easy. It's 1 plus 1f, so it can take the value. Let me put it here. So the M total can be 3f's for that one. Here it's 0 plus 1f, so you get 1f. Here it's 0 plus minus 1f, so you get minus 1f. And finally, I think it's obvious, you get here for that one the minus 3f's. These numbers are the possible numbers when are the possible quantum numbers for these bases here. And from them, you can now guess what is the quantum number S total. For that, let's construct a diagram analogous to the diagram that we introduced in last lecture. So let me erase this and make exactly the diagram again. So the diagram was, well, let's see. Let's see. On the horizontal axis, let's put M total. M total. On the vertical one, S total. Let's now mark here the values for the M total that we just found. So like this. Like this. This is not doesn't have to be very straight, because you only need the structure of the diagram. Minus 1f and minus 3f's. Okay, I don't know if you can see it here. So it's plus 3f's here. Now, let's imagine for the moment that S total was 1f. If it was 1f, then, because we know this, if S total was 1f, then M total would be minus 1 and plus 1f. So minus 1f plus 1f. So it's fine. It agrees with our findings here. Now let's guess, what if S total was 3f? Then, by this rule, we know that M total must be between minus 3f's and plus 3f's in steps of 1. I forgot to mention this, of 1. And so, in the diagram, well, between minus 3f's and plus 3f's in steps of 1, well, we have something like this. This one, this one, this one, and that one. So in conclusion, S total can only be 1f and 3f's. By the way, why can't we go further with this? Can you see? Why can't we go further? For example, why can't we go further? Because you see, as soon as we increase the S total, as soon as we increase to S total to 2, for example, then the M total would be between minus 2 and plus 2. But we do not find any plus or minus 1, plus or minus 2 here. So we have to stop at this layer. Okay? So this is how we find. By the way, from this diagram, if you look carefully, we would figure out a very important rule that I did not use, but it's encoded in the diagram, which is the S total, in general, is always between the S12 minus J3, and it's also between the S12 plus J3, again in steps of 1. So you can also find what are the possible values here just from this rule. Okay, S12 is what? It's 1, right? So this is 1. This is minus 1f. So the minimum value is 1f. Here it is. But 1 plus 1f here is 3f's. So we have that one. Well, you can only go in steps of 1. Well, but between 1f and 3f's, it's 1. So it's fine. You can either construct a diagram, which I prefer, by the way, or you can use this. The diagram is I prefer the diagram for a very simple reason, because now I want to relate these bases for this CSCO here with the basis for that CSCO, which is written here. So we want to relate these dots with those dots. And the diagram makes it easy to do that. Why is that? Let's erase a few things from here that we no longer need. Because this, by the way, is the most difficult part of this addition of angular momentum, is to relate those two things. It's more difficult because it's easy to make mistakes. Because the calculations can quickly become complicated. And if you're not, because you don't want to write everything, you just want to suppress indices, and that might lead to mistakes. But let's do one step at a time to relate those bases. This is not needed as well. So we only need these two things. The first key observation is very similar to what we did previously. Well, is to identify the subspaces here. Here we find the EM is equal to 3F. And by the way, here is M total. M total is equal to 3Fs. Here we find the M total is equal to 1F. And of course, here is M total is equal to 1F here. And so on. I think you can find these subspaces, very important ones. That one is the M total minus 1F, which is found here on this column. Notice the dimensionality is the same, right? So the subspaces, so this basis must be related to that basis, and so on. And finally, the M total is equal to minus 3Fs, which is found just here. It's one-dimensional, so it's just like a line. So M total is equal to minus 3Fs. Good. Now let's try to relate these bases, because I think it's easy. Those two vectors here, these basis vectors, must be the same. So let's write that. The first key step in all of it is to relate the one-dimensional spaces. So we know that this state here, M total, is equal to 3F. So M total, let me first write the S, because this is the order that we are used to. So S total is equal to 3Fs, and M total is equal to 3Fs. Of course, this basis ket must be that basis. And that basis, well, it is M12 is equal to 1, tensor with M3 is equal to 1F. Fine. Now, you must now remember this from last lecture. Here is S total is equal to 3Fs. And we know, by the way, before I'm moving into that, by the way, here is E total is equal to 1F. Fine. You must remember now that now you have the ladder operators, which allow us to map the states in each one of these layers. So because when you act with a ladder operator, the S total is fixed. It does not change, but the M total does. So when you act with now the S total minus, you get this cat. Okay? So let's act with S total minus on this cat here, on this side, on that side, and try to see how this cat is related with as a linear combination of these two states. Can you see? This E M total 1F is that one. So let's do it. So now we just act with S total minus on this state. So the S total 3Fs, M total 3Fs. Well, is going to give us what? Let's see. Need to remember the rule before I do anything. Let's just remind ourselves of the rule. So the S total minus. In fact, let me just write the general rule. The general J minus that we saw when it acted on the Jm. This is general now. Was from the first lecture was h bar, a complicated calculation, and then J m minus 1. This complicated number is just J plus 1 minus m minus 1. Of course, though, if it was a plus here, it was a plus here, and this is a plus. But we are not going to use the ladder operator, just the lowering operator. Moreover, we also know, I did not say, but I'm saying it now, that S total minus is the same thing as you see, you need to specify how S total acts on this tensor product. So it S12 minus plus S3 minus. This is a given now. Now let's use those two rules in red and make this calculation. So it is a complicated number times this thing. The S total remains the same, 3Fs, because as we are still on this layer, and then M total is reduced by 1. So it's 3Fs minus 1, which is just 1F. So M total is equal to 1F. The same number that you find here on this column. See, M total 1F. You are here. Now let's compute that number. So the J is now, the S total plays the roles of the J's. So it is 3Fs plus 1. That's fine. Minus the M total. Now the M total is playing the role of small m there. So it's 3Fs minus 1. Now let's do this calculation carefully, because this is usually where mistakes are going to occur, is on these kind of calculations. So you get 3Fs here, you get 2 divided by 2, which gives us 5 divided by 2, minus 3Fs. Now if you subtract 3Fs minus 1, it gives us 1F here. And then, well, it just multiplies 15 divided by 4 minus 3 divided by 4. This is 12 divided by 4, okay? And this is equal to 3, right? So this is essentially the square root of 3. Let me put it here. Square root of 3. Okay? Here, let me just put it as total equals to 3Fs. M total is equal to 1F. Fine. Now, it just acted with S total on this side. Now let's act with S total on that side. But you see, To know how S total minus act on that side, we need to know the fact that S total minus is equal to that, because you only know how this thing acts on that side. So let me write it, S12 minus plus S3 minus. This is, by the way, the most tedious part of the entire task, is to write all those things. The idea is not complicated, it's just there is a lot of calculations to do with this thing. Of course, this one acts on that one, and that one acts on that one. So let's do it. By the way, I'm just doing in detail this one, and this one. The others I'm giving is homework for you. That one is also obvious. So I'm going to do just this one in detail and that one. Just like I did also in detail in the last lecture. Then everything else is the same ideas. Just do the same thing again. So let's just finish this calculation and then do that. So let's do this one. This one acting on this cat gives us, let me do this in detail, S12 minus acting on this cat here, plus, this plus, by the way, is this plus here. I put it in red for you to see. And then the S3 minus, and then the cat again. Can you see? Now we have these two things to compute. Fine, let's do it. Let's do it here. So this cat now acts on that one, and this acts just on that one, because again, these are extensions into the tensor product. So let's do this one. So when this acts on this, and it gives us, well, the h bar square root, let me put the square root smaller, and you get the M12 minus 1, which is 0, tensor with M3 is equal to 1F. What is this number? Well, you must remember what is S12. S12 was what? You see, this role, the S12 now plays the role of J. It was 1, right? So it's 1 plus 1, this part, minus 1 minus 1, that one here, plus here, I need to erase this part here, the top part here, plus this one acting on that. So what we get is essentially, well, h bar, a constant, and then this cat here. So the M12 is equal to 1, tensor with M3 equal to 1F is equal to 1F minus 1, which is minus 1F. So M3 is equal to minus 1F. Now let's get the constant again. So it's S3. So instead of a J, it should be here J3, but J3 is 1F because it's an electron. So it's 1F plus 1, minus now the quantum number here. What plays the role of the M there is the M3 here. So it's 1F minus 1. So far so good. Now it's just compute the constants. Let's see. The memory card went out, so let's keep going. We are about to compute these numbers here. Well, they are quite easy to see. This one is going to give us the square root of 2, right? Because these 1 minus 1s cancel, so you get just 1 plus 1 times 1, which is 2, and you get the square root of 2. Here on the other end, this number here, well, 1F plus 1 times 1F is 3/4, and minus 1F times 1F minus 1, well, it's 1/4, so 3/4 plus 1/4 is equal to 1. So this is a square root of 1. Now that we have these numbers, all we have to do, well, is to join this formula here, which is the left-hand side here, when S total minus acts on it, the lowering operator, And when the lowering operator acts on this side, it gives us here, this thing, which is that. So you need to equate now the following thing. This part is equal to this part, right? So this is our goal now, is to relate those two things. Now let's do it. Let's do it here. It's easier to do it here, like that. So this part here, well, you can see the h bar cancels with that one and with that one. You divide this side by the square root of 3, so you get the square root of 2 divided by the square root of 3. So let's write it. So you get here S total 3f's here, m total 1f, this part stays, is equal to, well, to this part, so the square root of 2/3 here, this thing divides that, times this, so m12 is equal to 0, tensor with, well, m3 is equal to 1f, plus 1 divided by the square root of 3. So 1 over the square root of 3 times this part here. So m12 is equal to 1, tensor with m3 is equal to minus 1f. So we just found out what is, well, what is this ket here, this state, for this basis, for the basis of this CSCO, well, just written it in terms of some linear combination of those two basis kets of the old CSCO, right? Whose coefficients is, well, that one and that one. Combines those two ingredients. Now, our goal now is to find this state here. We need to find that state. But how are we going to do that? Well, we find this state by first identifying what is its properties, or what is the constraints that this state must obey. So let's identify them. So far let's erase this, our calculations. We already have seen this first connection between the new basis and the old one. We already have here in blue the second connection. And now let's construct the third one. The third one, well, we need to identify what are the properties of this state. Well, we know that this state, because it belongs to this subset here, let me write it, this subset here, which is the E, which is the E, m total is equal to 1f. So it belongs to this state, this ket here. So that tells us something. It tells us that S total is equal to 1f here, and M total is equal to 1f, must be some linear combination, well, of these two basis kets, right? Because this subspace here is also E M total is equal to 1f here, just like this one. So let's write it. It's C1, some coefficient that we still have to compute. So it's C1 times this ket, and this ket is M12 is equal to what? To, can you see? Here, 0. Tensor with M3 is equal to 1f plus C2 times the other one, right? M12 is equal to 1. Tensor with M3 is equal to, can you see? Minus 1f here. Minus 1f. So far, so good. This is the first property, because this state lives in this subspace, and so must be a linear combination of that. Moreover, we want also that these coefficients here, well, must make this ket to be normal, right? We want it to have length 1. So the second constraint is C1 square, whatever these complex numbers should be, well, they must obey this rule, right? to make this a normalized cat. Moreover, well, these are two basis cats, so let's make it orthogonal to that one. So this cat must be orthogonal to that. So the S total is equal to 3f's m total is equal to 1f, dotted with S total, that one, is equal to 1f, m total is equal to 1f, here. Well, let me see, yes, correct. This thing must be 0, right? Now, we need to find C1 and C2 such that this thing is true. Well, I think in this case, well, you can quite easily to find it for this particular case. You can actually guess what is the answer. Let's try to guess it, because previously I already gave an example of how to do the calculations and derive it. This time let's try to guess it, because you see you already have the answer here. So for example, this cat is this cat, right? And this cat is that cat. So far so good. So if I make C1 into, can you see, 1 over square root of 3, and C2 minus 1 square root of 2 thirds, can you see that this thing is obeyed automatically? Can you see? Because then when you dot the thing, this one will dot with this one, right? And that one is going to be dotted with that one, so it gives us 1. So you get 1 over square root of 3 times the square root of 2 thirds here, and then minus square root of 2 thirds times square root of 3. Those two cancel, right? So this is in fact the answer. These two real numbers satisfy all these conditions. Moreover, by the way, they also satisfy this one, because those two already satisfy this condition that we had, okay? So it's fine. So we have a second answer. We already have now all these basis cat. How is it related to the basis cats from the old CSCO? So the answer is this one. So let's summarize the answer here. So I put here 1 over square root of 3, and here minus, it's a minus square root of 3 thirds. Let's erase this, because now, well, I'm not going to do it, because now you just use the same ideas that we had previously. Because how do you express this basis cat here in terms of this linear combination? Can you see? Because this set belongs to this one, the EM total is equal to minus 1f, the same subset as this one, EM total is equal to minus 1f, so this thing is a linear combination of that. So what we are going to use, well, what you should use is again the S total minus, just like we did from here to here, you do it again, acting on that one. That one is this one. It's a more complicated calculation, but you can do it. Act on that one, you get this linear combination, which is some linear combination of these two basis cats. Okay? I already have the answer here. I'm going to give it to you, the answer, because I'm not going to compute it. So this basis cat here, that one, which I'm going to write as S total is equal to 3f's, M total is equal to minus 1f. After acting with S total minus, what should we get? Well, we get this. After a long calculation, 1 over square root of 3, square root of 3 is equal to, well, let's see, m12 is equal to minus 1, tensor with m3 is equal to 1f. Can you see? Plus square root of 3 thirds, m12 is equal to 0, tensor with m3 is equal to minus 1f. Can you see? This basis ket here, the m12 minus 1, it's here, plus 1f, it's here. Can you see? This ket here is that one. Well, this ket, m10 is 0, m12 is 0, and m3 is minus 1f, it's that one. So with those two coefficients, you can find the answer. Moreover, how do we find that one? Well, you just identify the properties of it. Well, it's some linear combination of these two kets. It must be normalized and must be orthogonal to that one. So after putting those constraints in, solving the equations, you find that the S total, you can already guess it because I already have the answer here. S total is equal to 1f, m total is equal to minus 1f. Well, what should it be? You see? It's similar, right? It's similar to that one. Can you see here? How you obtained this expansion from that one? Well, look at it. Just choose the first coefficient to be the square root of 2/3. m12 is equal to minus 1. Tensor with m3 is equal to 1f. And then use minus 1 over square root of 3 times, well, what you find here, right? So m12 is equal to 0. Tensor with m3 is equal to minus 1f. And that's that linear combination. Well, of course, the final ket, what should it be? Well, this one lives in one-dimensional subspace. The E S total is equal to 3f's, or the E M total is equal to minus 3f's, which is the same thing as that one. So in conclusion, what can we say? What can we say? Well, what we can say is this. Well, let's write it for the last one. It's quite easy. So the S total is equal to 3f's, and M total is equal to minus 3f's. Must be that one. So it is the, let's see, m12 is equal to minus 1. m12 is equal to minus 1. Tensor with the m3 is equal to minus 1f. Minus 1f. And that's it. We just found all the connections between the new CSCO and the old one. Can you see? All in this entire list. So this is the first one, that one, and so on. Can you see? This one, let me see. One step at a time. This one here, it's that one, right? So S 3 divided by 2 and 1f here. Can you see? And then this one is that one, and so on. Now, there is still one thing left for us to do after all these calculations. You see, let me erase. I need to erase this. Because we must remember where our starting point. Because our starting point was adding the intrinsic spin angular momentum of the electron 1 and the electron 2. And that gave rise to the quantum number, to the operator S12 squared. And if you still remember, we know something. We know something. Let me see. Let me remind you what is the triplet. The triplet allow us now to rewrite, let's see. The triplet now allow us to rewrite this ket here, m12 is equal to 0, m12 is equal to 1, and so on. Because remember, the triplet, again, this is not working. Let me see. Let's put it in green to make this thing work. Okay. So the triplet, remember the triplet that we already knew. So the triplet told us, that we derived in last lecture, told us something very important. That S12 is equal to 1, M12, is equal to 1, is written as M1 is equal to 1F, tensor with M2 is equal to 1F. More, S12 is equal to 1. Of course, S12 is also always equal to 1 because that's our assumption. That's why we decided that the first two electrons that we combine belong to a state, one of the triplet states. So S12 is again equal to 1. So this is M12 is equal to now to 0. And recall this was 1 over square root of 2. Now, M1, this is longer. It is minus 1F. Tensor with M2 is equal to 1F, right? And then you get a plus here. So you get a plus, and you get M1 is equal to 1F. Tensor with M2 is equal to minus 1F. Very important formula. And finally, the final element of the triplet was S12 is equal to 1 again, but in this case M12 is equal to minus 1. So what you get? Well, you get the M1 is equal to minus tensor with, I hope you can see it, M2 is equal to minus 1F again. And now our task, that I'm not going to do, but it's quite easy, is just substitute here. For example, you have this state M12 is equal to 1. That corresponds to that one. So you can replace this part by this tensor product. You just bring it here and put it here. Can you see? Let me just do this particular case for you to see. Let me write it. If I bring this part here, so this state here, I'm just going to replace this by what's written here. So it's M1 is equal to 1F, tensor with M2 is equal to 1F. That's it. You get something like that. If we had used a much easier notation for this, we would write this cat as follows. So under the easy notation, there is let me first write. So we'll write something like this: up, 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 and that's it. Can you see? Using the arrow notation here. So up, up, and up. Can you see? You can do for the other ones. Just replace it. So this is up, up, down, and down, down. You just replace the plus or minus 1F by arrows. But in this calculation, we did not use that, so you can see exactly what the quantum numbers are all the time. Of course, even in doing that, we already suppressed many quantum numbers from here. For example, we've suppressed the J's here, the J1 and the J2 and the J3, which, of course, because these are electrons, is always 1F. So this is how you add angular momentum. So how you add angular momentum in quantum mechanics. You add the operators, and now you have to find the eigenstates. You need to find need to define those eigenstates for those new operators. Of course, you need to add other operators, so you construct a CSCO. So that's how you do it. You use the CSCO to define that basis. But of course, you have also the old CSCO, where the angular momentum is still not added. And you want to relate the eigenbasis for this CSCO with the old one. And all the difficulty is in relating those two bases that which we find here. Of course, we just added, essentially with these formulas, you have the eigenstates that describe a system with 3 electrons. Okay, you first added the 2 ones. I chose a state for those 2, and then I just add the 3rd electron on top of it. And these are all the states, given that the first 2 electrons must be in S12 is equal to 1. Of course, you can choose also S12 is equal to 0 and do these calculations again. But the same strategies that we used here are the same. So this is how we add. This is what it means to add angular momentum in quantum theory. I hope this has helped, and the same strategy you can use for any addition. So see you next time.